The exciting world of statistics continues. So what have we done so far? In Module 1, we looked at what statistics was in general and what data was in general. Then in the previous module, we talked, in Module 2, we talked a little bit about how to describe the dispersion of the data, meaning the spreading out of the data. And we did that both graphically with things like histograms and whisker box plots and things like that, but also we talked about a few key terms, those key terms being something like the mean, which is the average, the median, which would be kind of the middle number if you rank order it from lowest to highest, the mode, which is the thing that occurs most frequently, the quartiles, which means like the 25th percentile, 50th percentile, 75th percentile, and then just percentiles themselves, like first, second, third, fourth, fifth, sixth percentile, and so on. And then we also talked about standard deviations, where the standard deviation was talking about what kind of dispersion we had on average. So where we go from there is in Module 3 is looking at probability. How can we use statistics and use data to try to predict if something else will happen? Because quite frankly, what's the point of doing statistics if you can't predict the future? Oh, kind of like the movie Back to the Future. Okay. It is indeed true that we can calculate the probability of a meteor shower. Yeah, we're just going to talk basically about probability. I'm not watching these videos. I'm assuming if you want to sit down and watch an 11-minute video and you've got nothing else better to do, go to town. I can't even say I'm going to do it because I'm not going to do it. And I'm not going to lie to you about watching it because I'm better than that. Okay, so let's start to talk about what is probability. So probability is trying to make a prediction, basically. And it's trying to be a probability is a measurement of a particular outcome from a certain activity. So the classic one would be flipping the coin. So flipping the coin itself would be the activity or the experiment. And if I want to get heads 2 times in a row, having flipped it only twice, I could calculate the probability of that. And what we see here is that, right, the coin itself is controlled. It's a controlled experiment because it's only got 2 sides. It's got a standard sort of weight. But we don't know the outcome until the coin is actually flipped, meaning it is a chance experiment. Now, we already know what the outcome is. The outcome is that if I flip the coin, I'm either going to get a head or I'm going to get a tail, one or the other. The sample would be all of those possible outcomes. The possible outcomes, I suppose there are 3, technically speaking. It could be heads or tails, or it could land directly on its side and be neither heads nor tails. But more likely than not, we're just talking about heads or tails. We can represent all of those possible options, meaning heads or tails. We can do that by either listing all those options, heads and tails. We could create a tree diagram, or we could create a Venn diagram to describe all these things. And we'll talk about these very shortly here. But again, for one example here, we could say that the sample is equal to either heads or tails. Sorry, I thought they were actually going to do it. Tree diagram. I was going to try to draw on this, but it's probably, I can already tell, it's probably a disaster waiting to happen. Okay, I know what a tree diagram is, but I can't draw it quickly enough. Um, you know, I suppose if I did know it, I could go to this Khan Academy video. But basically what you would say here is that you would have a... Okay, I'm going to click on images. It could be offensive what you see. I'm just going to click on it. Dude, you never know. What weird people. Hey, perfect. Math is indeed fun. Flipping the coin, I've got a 50-50 chance. 50-50 chance of getting heads or tails. And then if I flip the coin twice, I've got a 50-50 chance of getting heads or tails. So notice that flipping the coin heads twice in a row, the first time it happens has actually no impact on what's going to happen the second time, because each of those two events are independent. So what a probability tree does is it looks like a tree. It's kind of spreading out from that one single point. With, again, the outcomes listed here, the probability of those events each being here. And they're each equal because it is pretty much equal whether you'll get a heads or a tails based on flipping the coin. Let's go back to this. Or you could create a Venn diagram. In this case, a Venn diagram, those are kind of those circles. In this case, the circles would not be concentric with each other. Again, I know what it is. I'm just going to see here if it can give me it really quick. But it wouldn't be... this is if you're flipping it twice. I guess we could do it this way. It's fine. If I flip the coin twice... then I could basically get 4 different options. I could get one where it's head and tails. I could get one where it's tails and then heads. I could get one where it's head and heads. Or you get one where it's tails and it's tails. So you notice here that if the coins have a head, they could, again, overlap each other. Tails are outside of it. As opposed to over here, if I'm talking about the coins having tails, tails, heads, heads, tails, they could be concentric around tails, or I would have heads being outside of it. Hey, dude, look at this. It's even from OpenStax. Actually, it's from... Actually, know this guy, Anthony. He's a really nice guy. Lives in Houston, Texas. Very nice person. He brews his own beer. Fun fact. He's one of those guys, though. The guys kind of that has the time and the resources to be doing those things. He cares about those things. Dude, I'm just trying to survive here. I don't have time to make my own beer. Okay. We kind of already know these things here. Again, an event would just be what is the outcome. If we start to have 2 events happening, then we could have multiple events. And then we just want to know how often is such an event going to happen. That would be the probability of our outcomes. Most of the time, the outcomes are equally likely if it's an experiment where things are quite random. So again, if I'm rolling a dice and it's a 6-sided dice, then each of these 6 options are just as likely as the other. If I toss a coin and the coin is fair, then you're just as likely to get a head or a tail. As is true as well. If you randomly guess true or false, and the professor doesn't have a preference for choosing one or the other, then you'll probably get a 50%. I've noticed I choose a lot of C's for some reason, but I don't know why that's the case. Okay, so how would we describe this kind of thing happening? If each event is equally likely, then I could say something happening. Let's say, in this case, if I toss a fair dime, meaning a dime that's equally likely to be a heads or tails, excuse me, and a nickel that's equally likely to have a head or a tail, then my options would be a head for the dime, a head for the nickel, a tail for the dime, a head for the nickel, a head for the dime, a tail for the nickel, or a tail for the dime, a tail for the nickel. Okay. 4 outcomes. So the question then here would be, what is the number of outcomes where I could get event A, where event A is getting at least one head? I could get one head here, or I could get one head here. Okay, so there are two options where you get at least one, where I only get one head. So there are 4 possible options, so 2 out of 4. So there's a 50% chance of getting at least one head. Seen another way, what if we roll a 6-sided die, and let's say we want to get the event being something where I want to get at least a 5. That would mean there are then 2 outcomes. I could get a 5 or a 6. To get a 5 or a 6, that would be 2 options out of 6 possible options. So in this case, we have a 1/3 probability. Now, as the last 2 paragraphs point out here, that in reality, if you only flip the coin a few times, you might not actually get that to happen. You really have to do it a fairly large number of times to get that on average. So it is possible to flip a coin 5 times and get heads all 5 times, even though it should have been a 50% chance of getting tails each time. But you have to do it at least, we're talking about large numbers here, large number of events happening. Here's a more detailed example that I'll let you read on your own. Except to say, again, numerator is saying how many possible outcomes are there as a whole. There are 150 different jelly beans, 26 of which are blue. So I can solve that ratio and I'll get my percents. To have something fair is actually pretty difficult. It turns out that it's actually a little bit more likely, depending on the coin that you're flipping, most of the time that you will get heads over tails. So, just for your own purposes, if you're going to bet someone on a coin flip, you should generally choose heads. Can't say you didn't get your money's worth now in this course. You can now go to Vegas, the 9th island, and professionally gamble. And I don't know, I doubt that there's a table where they just flip coins, but that'd be pretty cool. Pick heads. Same with dice. Dice are also not equally likely. This isn't going to be on the exam, so I'm not going to waste my time. Dice are not fair either. Again, I didn't make these slides. Don't blame me. Not my fault. What about when the outcomes are not equally likely? So let's look at something where you get a surgery done, where most of the time getting the surgery, most of the time it is successful. So let's say that getting a surgery done has an 85% probability. And now I want to know, what's the probability that if the doctor conducts 2 knee surgeries, that both will be successful? Okay. So let's look at what all the possible options are. The surgeon could do both surgeries and be successful both times. It could be successful the first time and fail the second time. It could fail the first time and succeed the second time, or it could fail both times. But what we know is that these are not equally likely. And the reason why they're not equally likely is because failure only has a 15% chance of happening each time. So it's already unlikely. Having success both times, that's something that happens with an 85% probability, and then the second time an 85% probability. Which is why when a doctor does surgery many times and you ask them, do you think it'll be okay? And the doctor will say, well, I can't guarantee it, meaning it's possible you could be one of the Fs. You'll probably be okay. Meaning you're more likely than not going to be an S. So it's not a 1 out of 4 chance that you'll be successful just because there are 4 options here. Because each of these do not, success S or F do not happen with 50% probability. In fact, it's 85%, 15% probability that they will each happen. Meaning that it would be 0.85 times 0.85, which, if I have my handy calculator out here, meaning you've got a 72.25% chance of success both times, as opposed to a 12% chance of success and then failure, or a 2.25% chance of failure both times. A 2.25% chance of failure both times. So more likely than not, the doctor will be successful both times. Then we have the things where it's A or B or A and B. And really there it depends on whether the outcome for one is dependent on the other, or whether the two events are independent of each other. And what that's going to do is it's going to determine how you calculate the probability of something happening. In this case here, if it's A or B, meaning something can't be both A and B, then if it's 1, 2, 3, 4, 5, and 4, 5, 6, 7, 8, 4 and 5 can't exist here as well as exist here. Meaning A or B would be 1 through 8, 4 and 5 not being listed twice. If it's A and B, then 4 and 5 can be listed twice. So that A and B have only those two cells, 4 and 5, meaning they're listed twice. 4 and 5 would be where A and B are both existent. Obviously, you can count cards with the skills I'm teaching you. Now, what about complements of events? Basically, what are things outside of that event? So meaning, what are all, A prime is any outcome that's not in A. So if A prime is 5 and 6, right, then anything that's not in that would be 1, 2, 3, and 4. So if the sample size is 1 through 6, and A is 1, 2, 3, 4, then 5 and 6 would be the prime because they're not in the original set of A, but they are in the sample. 5 and 6 represent 1/3 of the sample, or 2/6. Now, the original set plus the complement need to equal 1 because that would be the entire sample. When things get a little bit more complicated would be conditional probabilities. So for instance, to get my job, you have to apply, then you have to be successful on the first round interview, then you have to be successful on the second round interview. Meaning that when we want to get just a single professor hired, we have to get 50 or 60 applications because people are dropping out and we're saying no to certain people. And for that one person to get the job, they have to have been looked at successfully by the search committee. The person has to want the job. They have to have done well in the first interview. They have to have done well in the second interview. And then they have to sign the offer letter. Meaning you need a whole bunch of things to go right just to get that single person. So let's look at it this way. What if I want to have let's say I have a dice, and let's say it's fair, even though we kind of know it's not. A die, I'm sorry, not a dice, a die. Let's say that the A is going to be 2 or 3. B is going to be 2, 4, 6. So what are the chances that we could get 2 or 3 and then 2, 4, or 6? What that means is that we would have, in this case, 3 possible options in our sample now, meaning the denominator itself is going to be 3 because we have 2, 4, 6. Right? Because the second time of it, we would have that. Then we need to find the number of outcomes where we get 2 or 3 in that reduced sample. Well, 2 is the only one that happens where you could get it to happen on the first and then get it to happen on the second and be in the second reduced sample space. So that's how we get 1 out of 3. That was a rough section, dude. Well, I've already shown you this, what the Venn diagrams themselves look like. I could have A and B or A or B. A and B is this joint space right here where the two Venn diagrams are share with each other. Ooh, there's this pretty funny statistical thing. For those of you who know me, I really don't care very much for politics. I don't care what your thoughts are about the world. You shouldn't care what mine are about the world. Scott Walker is a governor from the mainland, and he must not have passed this class. Actually, I don't think... Actually, you know what? He dropped out of college. There's... I don't know. There's rumors. You don't need to hear me say rumors. So just keep in mind this is a bad Venn diagram. In fact, the article here, I guess, says Governor Walker doesn't quite understand how Venn diagrams work. So this was saying that his administration, these are what the powers were. In the Evers administration, these are what the powers were. And he's trying to say in that middle space that they both have the same powers. Obviously, that's not true. What he should have done is put these in the middle here and then put different powers that each administration had over here. Because here he's saying A and B are the same, which I guess is what he's saying here. Oh yeah, look at this one. Oh, I've seen that guy in a movie. Yeah, it's the guy that like throws that little thingy. I don't know what this guy is, but I know my son watches him sometimes. Man, people are mean to each other. There's a lot of reasons to not be a politician. I suppose this is one of them. You get made fun of. You don't need me to... Oh, poor duck. He's got like a cast. He's got a crutch. A poor duck. Okay, let's go back to where we were supposed to be here. So there could be some things that are A that are not in B. Some things that are joint. That would be A and B. And we could also have it where outside of A and B, we could have A or B. So things here or here, here and here. Okay? So, given how we write this then, so this would be saying, what's the probability in this case? Would be, if we're in A, how likely is it that we're going to have B happening? So what we need to know here is that how likely is it that we'll be in A, and then what's the probability of being in both A and B? So notice here how we write this out here. Let me just go back here just because I don't want this to be lost here. Again, this is saying what's the probability that B happens given that we're in the A space. Meaning PBA is the area of B that is also in A. Meaning this joint space right here. So that would be, what are the chances that we're in A that whole A circle, but then more specifically that we're in this little part of the A circle. That would be our numerator. A and B over A. And we can use that and do some cross multiplication such that we can get it to be what's the probability of A times the probability of B given that we're in A. Now, what if the events themselves are independent of each other? Then basically being in one doesn't affect whether you're in the other one. So then would be, what are the chances that if you're in B, what are the chances that you're in A given for the B space? Well, what that would be in this case here would be, it'd be the probability of A, because A and B themselves are independent of each other. What's the probability of B being in the A space? Well, that's just going to be the probability of B. Again, because these are independent. What's the probability of being in both A and B? Well, that's going to be the joint probability. That's what I did to calculate, going back to that knee surgery question, that's how I calculated that it was likely those were independent outcomes. Unless the doctor is just having a bad day and he does the surgery on the same days, more likely than not, each time that that doctor conducts the surgery, each event is independent of the other. So what are the chances that both the surgeries are successful? That would be the 85% probability of success times the 85% probability of success. If they're not independent of each other, then we would say that they are dependent. So dependent would be saying, like, what if the doctor didn't go to class the day they taught how to do knee surgery? Well, now there's a commonality, bad doctor, right? And so now the chances that you have success and success, they're not, each of those events are not independent of each other because you've got a bad doctor. It's not just the randomness of cutting someone's scapula, or what's that called? The knee bone? Patella, right? Isn't it the patella? Where the chances that you... your kneecaps. Actually, I don't know how you do knee surgery. I'm not that kind of doctor. If it's a bad knee doctor, then the events themselves are not independent of each other. They're dependent because the person doesn't know what they're doing. Which is exactly how investigators determine that a person is a bad doctor. They look at what their success rates are. So, if the doctor is never successful at knee surgery, they're probably going to bring him in and have a little discussion of, hey, did you miss class any days? Did you show up on knee day? Did you take the exam? Because in that case, it'd be pretty easy to identify that the doctor is bad. Or you could have a bad nurse, or you could even have bad supplies. Now, what this also depends on is whether you have replacement. Meaning, once that thing is picked, that member of the population is picked, does it get thrown back into the pool or not? Meaning that it's going to change our probabilities of things happening. If we take something out and then don't replace it, then the sample itself has become one smaller. Whereas if it's always replaced with something else, the sample size remains the same. So here's our example of replacement in calculating the probabilities. If I've got a 52 card deck and I want to know how many spades there are, I don't know. Is that the one that looks like a clover? I think isn't that the clover one? Or is that the spear one? It makes sense. That would be the spear one. I don't know how many spear ones there are, but the chances shouldn't change if you put the card back in there. I'm obviously not a card player. If you do take it out and don't put it back in, now I've only got 51 cards remaining. And if that card I picked is a 3 of diamonds, right? Then my number of spears and my number of clovers are not going to change. But my number of diamonds are going to change because I have one fewer of them. And I have one less card. This is bringing back memories. I just remembering back to when I took statistics the first time, and as an undergraduate, I'd say my parents were paying tuition for me to be good at gambling, which is true. Fun fact, economists like myself used to have their annual conference in Atlantic City, which back in the day was kind of like the East Coast alternative to Vegas. I mean, it was pretty nice. It's where I had my bachelor party, was in Atlantic City, the AC. But the economists got kicked out because the economists would like do their like conference, they'd do all their presentations, then at the end of the day they'd go gambling. But because they were counting cards, they were like always, the house was always losing. So then they got kicked out. Okay. What about if events are happening that are mutually exclusive, meaning they can't happen at the same time? If the sample space is 1 through 10, A is 1 through 5, B is 4 through 8, C is 7 and 9, then what are the chances that A and B don't share any outcomes and that the sum is 0? Sorry, I have to look at this a little bit here. Because it's not entirely apparent to me what they're trying to say. Okay, so A and B shared space would be 4 and 5, 4 and 5. Okay, and then the probability of those happening would be we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9, 8, 10. So we have 10 possible outcomes. That's our sample space. We have A and B. That's 2. It obviously does not equal 0. So these are not mutually exclusive of each other. A and C themselves, there are no numbers in common there. So there's nothing where we could have it be in both A and C. So they are also mutually exclusive. The only thing we don't know, the only thing we, I think what they mean here is, I think there's an error here. I think this last line is incorrect. Again, I didn't make these slides. Don't blame me. But we know that they are not mutually exclusive. I'm not sure why they're saying it's not known whether they are mutually exclusive. We can actually prove that they are not mutually exclusive. And we proved that right here. So I'm not sure why they're saying otherwise, but I think they meant I think they mean B and C, if I'm not mistaken. Disregard. It's not going to be important for the exam anyway. It's just for your own theoretical understanding of things here. Okay, so let's flip the coin again. Let's say again the coin is fair, so equally likely to have heads or tails. Those are our 4 outcomes: heads, 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 tails, tails, heads, tails, tails. Each of these are equally likely. And let's say I want to get at most 1 tail. Meaning I've only got these 2 middle options where I've only got 1 tail. But I also have heads, heads. Because in heads, heads, I don't have more than 1 tail. I have actually 0 tails. So I actually have a 3 out of 4. I have a 3 out of 4 chance of getting A. Let's say that B is a chance of getting all tails. Well, there's a 1 in 4 chance there. We notice as well that B is the complement of A. So we know that the probability of A and A's complement is equal to 1. Which we also know as true as well is that 3/4 probability of heads, 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 tails, tails, heads. 4 is our sample size. 3 is those 3 outcomes. And the probability of its prime, or its complement, being 1/4, right here, would equal 1. Now, what if we're talking about things being mutually exclusive? Same situation. Coin that can be flipped twice. 4 possible outcomes, each equally likely. Now, let's look at C. C, the chance of being all heads. B being all tails, A being at least one tail. B and C, we would note, are mutually exclusive, meaning that there is no overlap in B and C, and that the sum is in fact equal to 0. Now what about these other events? D, getting more than one tail. E, getting ahead on the first roll. You'll notice here, and I don't want to go into all these details here because I kind of want you as well to read it and kind of have it make sense for you. Although if it doesn't make sense to you, you should send me an email and say, hey, Scheiding, slide 32. I'm trying to show the slide numbers here, keeping it like this, just so you can kind of see what slide number I'm at in the lecture. As kind of a way to organize this better. If it doesn't make sense to you, send me an email. I don't want to explain all of these because I want you to be able to explain some of it to yourself as well. But basically what we're saying here is that the only way it could get more than one tail would be having tails, tails. That's our 1/4. To be able to get ahead on the first roll, I could get this or I could get this. So that's a 2 out of 4 chance. I'll let you solve F on your own. Dude, go to town. Watch this dice video. Okay, so let's talk about some calculations here. And let's talk first about the multiplication rule. And let's talk about them being the two events in the sample space, A and B. Then in this case here, if I want to know A and B, it'd be the probability of B, then the probability of being in A if I'm already in B. We know that these are the same, as is implied right here. Then if A and B are independent of each other, then all I need to do here is multiply the two. Hence the multiplication rule. If they are instead mutually exclusive, again being mutually exclusive meaning that there is no overlap between the two, then I would have to do addition. It's probably easier to understand this if we have an actual example to work with here. Let's go on vacation. One is going to two places I've never been to, New Zealand and Alaska. You can only go on one vacation though. So what are the what's the probability that he's going to go to New Zealand? 60% chance. Probability that he chooses B, 35% chance. Now, notice it doesn't equal 1. So it could be that he's so indecisive he just chooses to go nowhere, which is a 5% chance. So, what are the chances that he goes on both? 0. We know it can't be both A and B because we know he can only afford one. We've already said what that is. So this would be B upside down U B. I don't know, I'll subscribe it to B upside down U B is 0, meaning they are mutually they're not mutually exclusive. Well, each of these two vacations themselves are mutually exclusive. Where the chances that he's going to go on A or B, because these are mutually exclusive, I'm going to use the addition rule, which would be 6 plus 0.35, meaning that's our 95% chance. So I at least go on one vacation. Let's go to the library. And let's be that I can check out a book or check out a DVD. Dude, who checks out DVDs anymore? So what are the chances that I go and get a book and a DVD, or the probability that I get a book or a DVD? Saying that the chances of checking out a book are 40%, the chance of checking out a DVD is 30%, and the chance that I do both here, the chance that of where we have in sample space B that we have an overlap with D being 50%. So what are the chances that I am going to both check out a book and a DVD? Meaning B, upside down U, D. The best way to say it, B and D. What's probably a B and D? Then what it's going to be here is that it's going to be the probability of B happening, which is 40%, times, because these are not mutually exclusive, the probability that I'm going to check out a DVD given that I've already checked out a book, which is 50%, as it's identified right here. 0.4 times 0.5 is 0.2. What's the chance that I'm going to do one or the other? This would then be adding the probabilities and subtracting the overlap between the two. 0.4 plus 0.3 minus the overlap between the two, because I want to get rid of that middle space in the Venn diagram where they overlap each other, leaving me with 0.5. Jeez, this is kind of dire. Well, let's do it. Geez, this is really sad. I didn't make these slides. 1 woman in 7, approximately 14.3%, will live to be 90 and develop breast cancer. Of those who develop breast cancer, the test is negative 2% of the time. Also, suppose that in the general population of women that the test for breast cancer is negative 85% of the time. So what are the chances of the, in essence here, the false negative, which is the worst case scenario? The false negative would be you get the blood test done. The blood test comes back negative and you're like, dude, I'm good to go. I'm not going to have breast cancer. And it turns out you actually do have it. What are the chances of that? So what are the chances that someone's going to do that? We need to know two things. What are the chances that the person has breast cancer? That we know is 14.3% of the time. How many times is the test negative? That's 85% of the time. Given that she has breast cancer, that's our B, what's the probability that she also tests negative? In this case here, it's multiplicative. Which we know over here, right? Multiplicative, we have a false negative 2% of the time. We're going to multiply that 2% of the time times the 0.143 and get the false negative 2.9% of the time. Pretty scary shit. Now, going back to this here, what's the probability that it's one or the other? What's the probability that she has breast cancer or tests negative, meaning that they are mutually exclusive of each other? Then it's going to be the additive rule minus the part where they overlap each other, the Venn diagram, the false negative, which we just solved for, giving me 0.9901. Notice how these build on each other. You are going to have to do that on the homework as well as on the exam. It turns out this is kind of a dumb extension of it because they're not mutually they're not independent events. The only way you're going to know that you have cancer or not, it'd be by doing testing. They're not independent events. And we know that they're not independent events because the probability of being negative is 85%. The probability of having cancer and being negative is 2%. Since these two are not equal to each other, they're not independent. Are they mutually exclusive? That's also not true. They're not mutually exclusive because the sum is not 0. So now let's start to build these probabilities into a contingency table. Meaning, try to create something where I have some conditional probabilities of certain events happening. So, is it the case that using your cell phone is dangerous for your driving? How likely is it that if you're driving, that your speeding is caused, in some sense, by your use of a cell phone? Is there any correlation even between the two? So, let's look at this. Those who use a cell phone while driving, 25 had a speeding violation in the last year, 280 did not. Those who do not use a cell phone while driving, 45 had a speeding violation in the last year, 405 did not. We use that to build up our sample here. We have 755 now in our total sample. Now we can start to build our probability here. How many people are cell phone users? That would be 305, right, that use a cell phone while driving. 305 over 755. Right, so it's going to be approximately a little less than half. What's the probability that the person had no violation and was a cell phone user? That would be my 280 here over my 755. What are the chances that they had no violation in the last year? No violation in the last year is my 685 over my 755. And what's the probability that I'm a cell phone user or someone who had no violation in the last year? I have to add those and subtract the part where they overlap each other, and I'll solve this. I could multiply these ratios by 100 to get the actual percent. I could also find out what's the chances of being a cell phone user given that I had a violation in the last year. The sample size, you'll notice, is reduced now to 70 because it's now just this column right here. How many drivers had no violation last year given that this person was not a cell phone user? Now the contingency reduces the sample size to 450. So now this row is dictating. So the given the whatever event, that given the is determining my sample size. Well, I thought they weren't going to give it to us, but it turns out they do. They just waited a long time to give it to us. Let's look at our tree and our Venn diagrams. Trying to understand what they're really trying to complicate this here. I don't. This isn't that complicated. I don't know why they're insisting on making it that complicated. Let's say I have two balls, a red ball and a blue ball, and I want to, I don't get what they mean. And there are two balls. Oh, I see. I'm drawing them from like a bucket, or I guess in this case we're calling it an urn. What are the chances I'm going to pick a red ball or a blue ball? Well, in this case, it's a 50-50 chance. And then if there's replacement, then it would be a 50-50 chance again. Obviously, if there's no replacement, then in 2 turns, there's a 100% chance I'll pick a blue ball, because I'll either pick it here or I'll pick it here if there's no replacement. Right, because red's now out of the question. In these tree diagrams, same thing. You can kind of see if I have many balls, where the chances of picking blue balls or red balls. We see the same kind of things here. I'm not going to explain it. I'm just going to assume here that we can read and we have some understanding of this graphically, or visually, I guess would be the right way to say it. I think you as a class depend on me a little bit more to explain the mathematics of things rather than the pictures of things. Let's go to the Venn. I'll explain it, and then I think we're going to be kind of good for trying to understand what's going on here. But again, if I'm skipping over a slide that is unclear to you, it's really as simple as emailing me. Anyone who's emailed me, I've generally emailed back same day, if not the day after. Just because this is a rather shortened class, I try to turn things around pretty quickly here. Venn diagram again. A or B or A and B. A and B is only this little space 6. A or B would be 1, 2, 3, 4, 5. Or B would be 6, 7, 8, 9. If you subtract the 6 out of it, right, then you've got the what are the chances of being in B given that I've had A, then it would only be 6. Oh, they're finally answering that. Jeez. It's kind of useful, but there's not a lot else here. There's actually nothing else really. Okay, so I'm going to wrap up this module. Again, what I'm trying to do is, you may or may not be reading the book, and that's fine. I'm not really expecting that you do it, but you should be looking at the slides at a minimum and trying to watch this lecture as I kind of go through the slides, just to have a better sense of things. And since this is an online class, unfortunately, part of the onus is on you to hopefully the video I provide for you like this and the homework assignments give you enough judgment to, or enough knowledge to be able to understand things. And if it's not sufficient, yes, you can go Google stuff, and I'm not stopping you from Googling and finding a Khan Academy or someone else who's made some other video, but I really am an email away. So if something is not clear, it's really as simple as emailing me. Out of the modules now, this is now module 3. This is where I sense that things are going to be getting a bit more difficult and things might be a little bit less clear. I am only an email away. If something is unclear, please, please, please email me.